Okay, hi everyone. We are Group A. Our topic is CubeSats. And first, we'll introduce what CubeSat is and describe the advantage and disadvantage. And third is the achieved mission. First, design specification. Five is requirement. And the six, future vision. And seven, concept of the first-time developers. Eight is our plan. First, let's introduce the CubeSat. Why the CubeSat is different from the standard nanosatellites is the shape is cubic. And why we build the CubeSat? Because it's more cheaper and allows students and researchers to design and build. And what's the function? The function include many experiments like Earth observation and amateur radio. And let's talk about the advantage. First is the low cost, because we can lower the budget from its design. And the second is its quick development cycle. CubeSat can be manufactured and developed using standardized design and commercially available parts within months or a few years. Three is the high tolerance of risk, because it's cheap, so we can do many experiments. Fourth is its multi-mission capability. CubeSats are well suited to a wide range of applications, including Earth observation, technology validation, communication, and scientific research, making them high adaptable for both commercial and research purpose.
So for the disadvantage is the limit size and the power due to the smaller size. So it has limited the space for the solar panel and the battery, which restrict the power capability that limit communication range and payload capabilities. So the next one is short orbital life. So usually launch in a lower Earth orbit. This results in short operational lifespan. After in a few years or a few months, they may burn up in the atmosphere while they are trying to re-enter to the Earth. The next one is vulnerability to space environment. CubeSat generally have a weaker resistance to the space condition like the radiation or temperature fluctuation, so it limits their reliability and shorten their mission lifespan. The third one is achieve mission. First is the Earth observation. It can collect Earth image and monitor the environment, like using the constellation of the CubeSat to provide high resolution image for commercial clients. The second one is technology demonstration. CubeSat often used for test a new technology in space. For example, like a NASA Macro A and B CubeSat that tests communication capability in deep space and explore the Mars. The third one is used for astronomy research, such as detecting UV and X-ray emission near Earth orbit. And the fourth is educational purpose. Many universities use the CubeSat as a tool to enabling students participate in satellite development process.
Okay, the next part is the CubeSat design specifications. So the first part is structure and size. This is the most important part for our class. And CubeSat have the kinds. It will separate to units, and the diagram, the graph in the right side is the 1 unit CubeSat design. And we still finding which unit we will use. Currently, our idea is use 3 unit, 3-unit design. And the second one is the electronic system, and this one is about the communication and power system, but actually this is not important for our class. And communication system is about the radio frequency we use in the cubeplates. Is also not important for our class. And propulsion system is about the size and the weight for the CubeSat. So if the CubeSat is too heavy, it need to more power to make it propulsion. And the payload is depending on mission requests, including compact carrier, sensor, and communication device. Okay. And the next part is the requirements. The 3 requirements is center of gravity requirement and structure and material, and the last one is mass and contact area. And the first one is about the center of gravity. Every different unit of the CubeSat need to have the different criteria of the center of gravity. For instance, the center of gravity for 1 unit CubeSat will be within negative or positive 2 centimeter of the geometric center. And about the material, the CubeSat usually use the aluminum alloys, such as 7075, such as this material. And the rail edge must be smoothly, so the minimum radius of need to be less than 1 millimeter. And the last one is mass and contact area. And the mass need to be from 2 kilogram to 24 kilogram. And the last one is about the contact area. Because the speed of the CubeSat is very fast, so it need to decrease the friction, so the contact area need to be as less as possible.
Okay, so let's talk about the future vision. First part, higher functional integration with micro miniaturization advancements. CubeSats will continue to improve in communication, processing, and energy capacities. And second, deep space exploration. CubeSat can be sent to the deep space to do exploration like Mars and Moon. And also NASA has already demonstrated CubeSat viability for deep space, paving the way for more complicated missions. Third, commercialization. Because of its low cost and versatility, and it can be treated as a product to sell to the customers who need it, and providing global coverage for communications and Earth observation services, such as Starlink and OneWeb. And this part, new materials and technology can be used. Like future CubeSats can incorporate advanced materials and manufacturing techniques such as 3D printing to improve radiation resistance and environmental adaptability in order to extend its lifespan and enhance mission suitability. And basic concepts for beginners. First, simplified design. A simple design improves launch opportunities to reduce the chance of compatibility issues during launch. Second, manufacturing and backup units. This approach helps mitigate risks of launch failure and allows the best performing unit to be chosen during several tests. Third, selection of familiar components. It can enhance reliability and also instills confidence in the launch provider. And this is our plan progress. First, just read the papers to get familiar with CubeSats, and we will choose a model to do analysis, including structure, stress and strain analysis while moving or being static, and how this CubeSat folds and unfolds in the space. Yeah, that's it. Thank you.
Okay, thank you. I only have one suggestion. I think you guys did a pretty good review of the QSEP design. Many important information was found. So I think now you can start to make designs of, for example, the uh, solar panel structure. So in the literature, they try to use origami structure. You can do the same. You can make your own design. I'm not sure how the software can handle mechanism design. Probably it's doable. So if you can design the solar panel mechanism as mechanism in the software, so they are not just fixed structures; they are movable design. So once you have that, you can show an animation of how the solar panel opens up and close. So that would be one thing I think that would be interesting for the project. Second thing is how much power that is needed to drive the mechanism, to open up the mechanism. So that would be something that is related to power. So once you have determined the required power, you choose a motor. What will be the required energy to create this kind of power? So that would be something that's worthy studying. And final thing, when you open up, uh, there is no atmosphere pressure in the space. So you may need to study about the space. Is there any force that is going to apply, like a wind? Is there something like a wind in the outer space? Maybe not. If there is no wind, then there's no pressure applied to the solar panel. Does that mean the solar panel will not break? So maybe study for that. Study for what could be the external force that applies to the solar panel. So if there is slight force or maybe large force applied to the panel, then you need to worry about stress and strain. So that will, I think those are the key directions that you can work on in the following weeks. So that's all my comments. So I will bring this to Patel.
Okay, thank you.
So that was say similar question that how the actuator will work. Like you have to design a CubeSat and how the solar panels will adjust to that CubeSat so that maximum spacing can be given to the devices which can be installed in that. Means you have to design like that. If you are designing like 3U design for CubeSat. So in 3U, how much apart from the actuator to operate the solar panels for power, the batteries installed in the CubeSat, how much space we can maximize it to install different sensors or for the uh, satellite purpose, for navigation, for other instruments to be installed. So we have to maximize the space. Accordingly, we have to design the solar panel which can be easily actuate. So you have to design like this. So you have to think on that idea. You have to review many of the CubeSats which are already sent to the space. And also you can think on like material selection. Recently, Japan is sending the wooden-based CubeSat. You can think on that. They are just to send with SpaceX in recent launch. So it's a wooden-based CubeSat. It was first world's wooden-based CubeSat. Wood is used as a material. So you can think on material selection. So it can be analysis in ANSYS. A different material selection like different composites which are already available in the library of ANSYS. Okay. Thank you. So now I request Group C to come and present their proposal.
Okay, so I suggest you do the opening remarks.
Hello everyone, I'm Professor and Professor Patel. So today our group is going to present our proposal for AMR for inspection. So the background and for this project overview is that FPCs or flexible printed circuits or soft circuits are produced and packed into rolls in factory assembly. These rolls can weigh a lot and can be very difficult for a human to carry and place it in a machine for automated optical inspection, since majority of FPC factories employ women. In this project, we aim to optimize an existing design given by the professor's lab, which is an AMR for AOI, to be more cost effective, but also maintaining its structural integrity and capabilities to carry heavy loads repeatedly without breaking.
Yes, so we're gonna talk roughly about the robot structure. So basically we divided the robot into two parts. So the lower one is the chassis layer and the upper one is application layer. For the chassis layer, is just a bit, you need to be stronger because it carry a lot of loads of the application layer. But in this case, in our project, we're not gonna do anything about the chassis layer. So yes, we're gonna change some parts in the application layer. So later on.
Okay, and then the entire purpose of our experiment is we carefully inspected the existing design, and we decided that the pneumatic structure of the gripper makes the robot structure way too complicated, because integrating an air compression system into the robot, I think it makes the structure too complicated. So we decided that maybe we can change a pneumatic gripper for an electric one, thus getting rid of the pneumatic system and simplifying the structure. Yeah, and there you can see like the old part of the chart and the new one. So yeah, that's our project, and that's what we are proposing. Yeah, just brief and short.
Patel, can you go first? Patel, can you comment first?
Yes. The first slide. This side, Professor? Oh, I'll be the first. Okay. So you are going to replace the gripper section, which was a pneumatic gripper in the case of our AMR, and you are providing like. But what does it makes sense for the structural differentiation? That what it will make some like low material for the selection for the structure, make it lighter. So how you'll prove that one?
Because pneumatic gripper, it requires a compressor, right?
Yeah.
Compressor is not, it's not light, right? So, and we remove it, and the entire, like, the pneumatic line, yeah, I think it's heavier than just the electric gripper and then like some controlling circuit. Yeah, it must be lighter and easier in terms of like service, because the entire robot is electric.
Okay,
Yeah, once
but
you replace the gripper with an electric one.
but what about like the weight of the PVC and FPC panels? Like how it can maintain the proper weight with electric? Have you select some grippers?
Yeah, we had a look at them. Yeah,
Hmm?
I think they're not worse than pneumatic ones. At
Okay.
least they're not worse, if not better.
Maybe we can check that how your design will change our original design, how it can effectively reduce the weight of overall components. And
Yeah.
what about the costing?
Costing?
Yeah,
I think.
have you review some that pneumatic and electric grippers about cost wise?
Depends. Maybe it might reduce. Depending on what we're using.
Because it's an AMR, so you have to select about like power consumption by your grippers, as power consumption by the pneumatic grippers and the
Yeah.
electric grippers, because it's operated by battery. All the full AMR is operated by the battery.
Yes.
So we have to think on that.
Yeah.
So all this analysis you have to do
Yeah.
before considering electric, because changing the gripper.
Yeah. We're just proposing. It's
Okay.
not like
Yeah.
it's a
Yes. Okay.
proposal,
Yeah.
Right?
No, it's my suggestion to go through all these parameters. Okay. Yes, Professor. Now,
Okay. So focusing on the gripper design, it definitely is okay. In the past, when I work on this project with my students, she actually tried different ideas. So this is what she ends up with. So that means there are some other possible designs. You don't really need to design a gripper. You can design something else. So please do not limit yourself. And what Dr. Patel mentioned was right. If you try to propose something new, we will be worrying about. We need to think about the details, such as what's the material you are gonna use. Okay, then does it cost more? And does it require more power? So if we want to propose something, we want it to be better, right? So please look into all details. It's okay to be crazy and propose something new, but based on that new idea, see if you can improve what we have so far. Okay, that's it.
okay. Thank you, Professor. Thank you, the group B, group C. So now I invite group B.
Okay, so we're group B, and what we want to do is to analyze the AMR with the robot arm. So this is the robot arm unit, which we have a robotic arm, and this one is a control unit. So we just count this as one unit, and also this base plate as another unit. And what we are gonna focus on is this wheel and shaft unit. So what we want to do is to analyze the wheel, mostly on the wheel and shaft unit. This is just like a demonstration, like a graph or something. And we want to know about the static structure analysis and also the stress and strain distribution, and also what the vibration and also deformation will act on the shaft. Because the whole robot arm unit and the base plate unit and also the control unit is gonna be very, very heavy. So it's gonna act a lot of force on the shaft unit, and we want to know like what kind of shape and what kind of material we should use for the shaft and also the wheels. And there's also another point we didn't put in the, our PowerPoint, is that we also want to like see what other kind of robot arm unit we could use on these systems. So this is our proposal.
Okay, so I think you want to work on the shaft system. Also, same as the previous team, when I work with my graduate student, she also a she. We spend a lot of time on how the chef system should be designed. So this is what she has so far. And again, this is not the best design. There must be something that we can work on to improve it. And let me tell you what's the current situation we have so far. The entire vehicle is like a metal plate installed on 4 wheels, and the 4 wheels are on the side, just like a crab. And there's nothing at the middle underneath the metal plate. So 3 years ago, when she designed this, it was okay, because at the time, the entire vehicle is around 500 or 600 kilograms in weight. But now it's over 1 ton, over 1,000 kilograms. So it's way larger than what she expected at the beginning. Now, although it's not damaging the plate right now, and it's not damaging the wheels right now, but a lot of load is applied. A lot of load is concentrated at the middle of the plate. So some students, after the first designer, decided to put something at the bottom of the wheel, of the plate. So there was a male student. He put, I think, 4 multi-directional wheels at the middle. But when he did that, the wheels will be spinning at the bottom of the plate, and that kind of spinning motion of the wheel will create a lot of torsional force, like a rotational force, to the floor. So sometimes that kind of torsional force will damage the floor. So after the male student, another female student right now, she designed something different. She used several metal balls at the bottom. So a ball applied on the floor is only single point contact. And there's always, it's just a normal force and friction force. So there is no torsional force, which solved the problem of this kind of torsional twisting on the floor. However, the metal ball are very hard material. So think about 1,000 kilogram, probably 800 applied to the balls. So each ball probably carries 200 kilograms. So think about 200 kilograms concentrating on the metal ball and then apply on the floor. The floor is still damaged, but this time the damage is not twisting time. It's just a normal force. So she right now is trying to figure out how to well distribute the load and try not to damage the floor anymore. So that would be something that we are looking into right now, how to distribute the load of the entire AMR. And of course, this
concern is very related to the shaft design. Okay, so right now, if you want to propose a completely new shaft design, you can probably even reconsider the plate design. Maybe the wheels can be placed somewhere else. I mean, yes, somewhere else. So you don't need to be affected by my student's design. You can be crazy. You can redesign the whole bottom plate, and all the wheels. You are free to do those kind of crazy designs, and as long as, I mean, and I should say, I hope whatever you propose and complete at the end of the semester can solve our problem. We don't want to damage the floor anymore, and we hope to use what we have so far to carry the heavy robot. And if possible, can you resize the entire vehicle? Right now it's too large. Okay, so please look into those and see if you can have something great at the end of semester. Okay, so back to you, Patel.
Yes, sir. Maybe you have already given them a good proposal that you can redesign the chassis by checking that it should not damage the floor. You can check our old design. We can provide you the results, how it is making changes to the floor. And you try to redesign the structure. Maybe you can reduce the motor with some gearing arrangement so that one motor can control both of the wheels instead of 4 motors which we are having. So you have to think that we can resize it with proper same robotic arm to be installed by resizing the whole chassis. So think on that. If you want to see whole design, it's available in Industry 4.0. Maybe you can just go and see the actual design right now and think on how it can be reframed. Thank you. Thank you, Professor.
Okay.
So maybe I can discuss with them on a free session so that if they want something. Yeah.
So only 3 teams?
Only 3 teams, yes, sir.
Oh, that's great. So one topic for one team. That is great. Yeah, please continue to have deeper discussions with them, and hopefully they can look into more details.
Okay.
Okay, thank you. I will get off. Thank you. Bye bye.
So maybe we can just, it's a general discussion. So for the first team like CubeSat, so maybe you are focusing on the structure of the CubeSat. So first, the CubeSat, which applications you want to install in it. So according to if you are designing 3U CubeSat, means 3 unit, the size is 3 unit. So now you have to think how this 3 unit can withstand how much load in it, so that how much components can be installed inside. So your space, to maximize the space, you need to have an origami structure so that all the solar panel will open in such a way that you can get a maximum space inside. Then the maximum space gives you how much sensors you can install it for different purposes, like some camera, some image vision or something, because satellite have different applications. So structure is like that, which gives you maximum application installation in a small satellite. So your curiosity should be design a CubeSat in such a way that the maximum space you can get for installing different satellites, different application layers on that. You want any questions from you? CubeSat? No? No queries? Okay. The group C, the AMR. I think you have seen the video of that AMR?
Like whatever it has in the presentation, then the presentation is the only thing we have of the.
No, have you seen the video of that AMR working?
No. Was that?
You have not seen? Have you seen the paper for that AMR?
No.
Okay, that AMR have a paper which we publish, the same AMR, which you have seen there.
Yeah.
We have published one paper on that. So maybe you can just search, if you can search my name, it will get it, or maybe in a Google Scholar. That paper we have published, so you can get the details of that. Some analysis we have done on that, like structural analysis and all. So it is already published in iRobotics. So, but the intention is like you are working only on the main layer, like application layer. So you think like why we are using pneumatic, because to control the proper gripper pressure, because we could not damage the panels.
Yes.
So the panels are in a roll form.
Yeah.
So if you make it from upside, you cannot pick it from upper side. You have to only hold it from the lower side, because it has a inner ring. Then the panel are roll on that.
Yes. Yes.
So you just need to hold it from inside.
Yes.
So now you have to think on that how much pressure electric gripper can control the pressure force.
Yeah, that's easy. Yeah.
So that is also power, like because that electric gripper has to be controlled through the power from the battery.
Yeah.
So all these things has to be properly done.
Yeah, but it understands once it's like. It's
Or maybe
stuck
you can
in the
propose a
chip.
new gripper design, new application layer.
Yeah.
Or you can you can think on new application layer instead of all this mechanism, because you know that the factor of safety is almost 28. It's too high. So all that material, all the chassis belongs to that, it was too high. So last year DMC group has proposed a new chassis design, which lowers the weight with the same payload and make it to 8 factor of safety. So maybe you can just redesign the application layer which can hold the similar thing, like all that is a metal plate in the, maybe this is there in Industry 4.0. It came back, yeah, you can see that one.
Okay.
See the design. It is Industry 4.0 right now. So you can just go and look how much metal plate is big. So maybe you can redesign whole gripping section to reduce the application layer weight.
Okay.
So then whole, or maybe the cost also. You can think on that. Okay.
Yeah. We might as well do that.
Group C, Group B.
Okay, group B.
Yeah, you want to work on AMR. Maybe you can see the AMR first, that actually how big it is. Have you seen it?
I think we have the image of how big the machine is.
Okay, but you have not seen it.
Yes. No.
Maybe one day you both group can go to the Industry 4.0. You can contact him and he will take to you there. You can see the AMR. The problem was you have seen the rotary chairs, the wheels on that, multi-directional wheels.
Yes.
They put 4 wheels before in 2021. The group of some graduate students, they put 4 wheels, but still the weight is too high. The weight creates the torsional force. It damages the floor because torsional force and the point load and the friction force together, everything is acting. They have damaged the floor. If the floor is like a normal cemented, it's okay. But if a floor has some matting, it damages that matting or some covering. So now what they are thinking of, like small balls in a group arrangement, so that only one ball at a time will be touched to the floor. So ball will not rotate, whole ball is rotating. So they have a series of ball on the whole ball. So it's only the one point it is touching the floor. Right now they have this arrangement. But maybe you can propose, like we have 4 motors for 4 different running the actuators. Maybe we can put some gearing arrangements, and instead of 4 you can use 2 motors and put some gears. to engage or disengage the wheels. So you can redesign the chassis so that this same load can be used for the similar chassis. The load, all the components and loads we are already calculated. So if you want, I can share you one paper which we have not published it, but we prepare it for a conference. So maybe you can check that they have all the descriptions. So I will give you that paper. So that have all the loading conditions, how much is the robotic load or how much maybe you can just analysis in that axis. Okay. Anything else you want to know about that robot? Okay. So if you guys anything else you want to know, you can just contact me or you can come to the lab anytime.
Yeah.
Okay.
We can read the paper first.
Yeah, you can read the paper first because you can also read the paper. But that is not published, that is published. So you can just have available online. And for CubeSat also you can refer me because basically I am an aerospace engineer. So you can just if you want to know something or you have some different idea, you can discuss with me. Okay. So I am always available in the 262, our lab, from 10 to night 9. So you can come anytime. Okay. That's all. Thank you. So next time, prepare the PPT. Prepare the PPT on time. Okay. I think next will be your project evaluation in mid evaluation will be once. Yeah, there will be one more presentation, your progress report.
Okay.
And then there will be a final presentation.